Hi everyone, welcome back to Section 3, Matrices. We're continuing our discussion from previous videos on manipulating matrices, but this time by performing basic calculations on them. So this video is going to go into a review of linear algebra techniques, linear algebra concepts, and using those techniques in our programming. I'm Ryan Lafler, and this is a video corresponding to Chapter 2 of the book, Climate Mathematics, Theory and Applications. So let's begin. In this first example, we're going to generate two matrices called A and B. First, we specify the set seed option. We're going to write the integer string 1, 2, 3. And what the set seed function does is it enables us to generate pseudo-random numbers. So what is a pseudo-random number? It is a number generated from a probability distribution that when I enter a seed value, such as 1, 2, 3, it means that you're going to generate the same random numbers that I generate. And it kind of goes against the concept of a random number, but keep in mind, the generation of it was random, but by setting a seed value, it means that we can replicate each other's results. So that's why we call them pseudo-random numbers, because the generation is random, but when we enter that seed number, we're going to get the same random numbers. In defining our matrix A, we use the matrix function, and defining the data that's contained within matrix A, we use the round function. Now what the round function is going to do is it's going to create whole numbers. How do I create whole numbers? I specify that I want 0 decimal places, so no decimal places, and that's specified by the 0. The data that we'll be filling matrix A with comes from a uniform distribution. And if you take a look at the highlighted portion, the runif command generates random numbers from that uniform distribution. So I want 100 random numbers on the interval from 0 to 100. So my minimum value is 0, my maximum value is 100, and a uniform distribution assigns equal probability to every single number within that interval. And I say interval because the uniform distribution, in this case, is continuous. So we're going to have decimal values that are inherent to the random numbers. And by using the round function, we are forcing those decimal values to be whole integral values. So I have 100 values, and I want to structure my matrix going back to the matrix function as having 10 rows and 10 columns. 10 times 10 is 100. We have 100 observations. We're going to format these observations into a square matrix of 10 by 10 dimensions. So let's run both of those things. Our seed value that we use in the creation of matrix A. And here we have for matrix A, printing it out in the above tab in RStudio, these values filling in the 100 spaces in matrix A. So if you were to write this command, set.seed, and the integral value integer string 1, 2, 3, and you create a matrix A just as I did, pulling from a uniform distribution 100 values, we're going to get the exact same values. It's the concept of a pseudo-random number, and it's used in data simulation and statistical simulation. Now let's set a different seed value, because if we set the same seed value and we pull from the same distribution, we're going to get identical numbers. So let's set a different seed value on the integer string 456, and they don't have to just be 3 units long. I just do that because 3 is a nice number and, it's used a lot. We talk in threes. In defining our matrix B, we set the seed value 456, again pulling from the uniform distribution 100 values on the interval from 0 to 100. We want whole values, and B is going to be another square matrix. So running all that, here I have matrix A, here I have matrix B. Matrix B is filled with different numbers, but because we set that seed value, you're able to replicate the results and get the exact same pseudo-random numbers that I did. We're going to use these two matrices in going through basic operations and basic calculations using these two matrices. Some of the topics include addition, subtraction, multiplication, division, element-wise, and in accordance with linear algebra techniques. So let's get started. In this first example, we're going to perform matrix addition. Now we can only add matrices or vectors if they are of the same dimensions. Since we have two square matrices of 10 by 10 dimension, we can add them together. So adding them together, we see in our output console this resultant matrix. And I didn't save it to a matrix because there just wasn't no need for these basic calculations. If I subtract two matrices, same story, same concept. They have to be of the same dimensions because this is an element-wise operation. Printing the output, matrix A minus matrix B gives us this resultant matrix that we just printed in the output. How do we see the number of rows and columns in a matrix? Well, we use the nrow and ncol command. And the number of rows in matrix A is 10, number of columns in matrix A is 10. And these commands, I think we even saw them in the previous video, are especially useful in automating processes. So let's say I want to iterate through a matrix of n number of rows and p number of columns. And I just say n and p because they're generic. Well, what the nrow and ncol do is instead of assigning a specific value, by calling these functions, I can automate certain processes so no matter what the dimension of the matrix, I can use those functions to just iterate right through it. So it doesn't have to be a specific dimension. It can be any dimension with any number of rows and columns. And by using these functions, I can automate certain processes, iteration techniques, things of that nature. So scalar multiplication of a matrix. Scalar multiplication involves having a single observation multiplied by a matrix of things. So 5 times A, recall here is matrix A, so that means 5 times 29, 5 times 79, 5 times 96. It's an element-wise operation. So we'll just run these and see them in the output. Here we have 5 times A, right? 29 times 5, 145. So this scalar, which is 5, is multiplied by our matrix A, and it's multiplied by every single element in A. Same with 4 times B. 4 is multiplied with every single element of B, and negative 3. Negative 3 is another scalar. It's just a negative scalar multiplied by every single element of A, and here we have it. So that's scalar multiplication. Matrix multiplication. In this section, we're going to multiply two new matrices that we're going to create, matrix C and matrix D. Again, using the setSeed function, we're going to generate pseudo-random numbers pulling from a uniform distribution. We want these numbers to be whole, so we use the round function, no decimal places. And these are no longer square matrices, but are instead a very long vertical matrix, which is C, 20 rows and only 5 columns. And we're going to have a wide matrix in matrix D, 5 rows and 10 columns, so a wider matrix. I run these two matrices and their creation. Here we can see C and matrix D. So matrix C is very long, matrix D is relatively wide, both filled with pseudo-random numbers generated from a uniform distribution. Let's examine their dimensions. So the dimension of C is that we have 20 rows, 5 columns. Dimension of D, 5 rows, 10 columns. Always remember from linear algebra that matrix multiplication only works when the first matrice's number of columns are equivalent to the second matrice's number of rows. So this is a hugely important concept. If you try to multiply two matrices where the first matrice's number of columns are not the same as the second matrix's number of rows, you're going to get an error. It's invalid, it doesn't work, because it's not possible. So that's a key concept of matrix multiplication, and we perform matrix multiplication by specifying the percent, asterisk, percent. So let's multiply matrix C by matrix D. And I also should note that matrix multiplication, unlike scalar multiplication like 5 times 4, 4 times 5, when it comes to dealing with matrices, the order of how you multiply things absolutely matters. So let's do that. Multiply matrix C by matrix D. And here we have a resultant matrix. So if this is your first time doing matrix multiplication, what happens is we just change the entire form of our matrix as well. So initially we multiplied a 20 by 5 matrix by a 5 by 10 matrix. The reason why that worked, we had 5 columns in our first matrix and we have 5 rows in our second matrix. By doing that, 20 by 5 times 5 by 10 matrix, we end up with a 20 by 10 matrix. So if you look, the dimensions of our multiplied matrix are now 20 rows and 10 columns. So matrix multiplication changes the shape of the matrix because we multiply the corresponding row of the first matrix with the corresponding column of the second matrix, and we add those up. So it changes the shape of our matrix, and it's not just a straightforward multiplication process. There actually is a bit of work behind it. So let's try that. Let's test if we can multiply, well, we can multiply C by D. Let's multiply matrix D by matrix C. Do we get the same result? And the answer is absolutely not. Remember that whole concept of we can't just order matters when it comes to matrix multiplication? Well, here's a prominent example of it. So why can't we multiply matrix D by matrix C? Well, we have a 5 by 10 matrix in D. So we do a 5 by 10 matrix and multiply that with a 20 by 5 matrix, we're going to have an error, because the number of columns in D10 is not equivalent to the number of rows in A. So the only way that these two matrices can be multiplied is if we multiply C by D, which is what we did in the first example. And that's just a review of basic matrix multiplication. We did the traditional matrix multiplication. Now let's see if it works with element-wise matrix multiplication. So instead of conforming to the first matrix having some number of columns and the second matrix having the same number of rows as the first matrix has columns, let's see if there exists an element-wise matrix multiplication in R. And it actually does. So if you remember matrix A and matrix B, and I'll pull those up, matrix A and matrix B were of the same dimensions. They were 10 by 10 square matrices. So let's do element-wise multiplication. And we're just going to print that out in the output console. So here I have 261 in the first place. Notice that the shape of the matrix didn't change. It's still a 10 by 10 matrix because we didn't perform true matrix multiplication. We performed element-wise matrix multiplication. So it preserves the shape because we're multiplying the first element of A with the first element of B. 29 times 9 is 261. Second element, or I should say be a little bit more specific, the second column first row of A with the second column first row of B. So 96 times 37, if you want to check it, is 3,552. That's the concept of an element-wise operation. So let's see if this works with matrices C and D. We know that these are of two different dimensions, so will element-wise operation work on this? Absolutely not. Because they're of different dimensions, we can't perform an element-wise operations, so that's why we get this error. They're non-conformable arrays. And when it says arrays, it's just being general. All a matrix is a two-dimensional array. There are three-dimensional arrays, four-dimensional arrays, so a matrix is a specific form of array. Next up, let's perform matrix division. So if there exists matrix multiplication and scalar multiplication, well then maybe there's scalar division as well. Turns out there is. So using matrix C, let's divide every element in matrix C by 4, and we get this result. So that's scalar division. Equivalently, you can multiply by 1/4 with the matrix C, and you get the exact same output. So division or multiplication, it's your choice when it comes to dealing with scalars. Dividing is an element-wise operation. There is no formal definition of matrix division. The closest that we can get is by taking the inverse of a matrix. So when I say that there's a division function in R for two matrices, I'm saying it's an element-wise operation. So if I were to divide matrix A by matrix B, this would be my output. Again, we have a 10 by 10 matrix. The reason why the matrix looks like this is because it still is a 10 by 10 matrix, but because we didn't round off on our numbers, and since when dividing by 29 divided by 9, we're going to get a decimal. I just didn't round the decimals, but this is a 10 by 10 matrix, and it was an element-wise operation. Let's try C divided by D. Again, we get the non-conformable arrays error because we're dividing, or we could be multiplying, by matrices that do not share the same dimensions. So element-wise operations like addition, subtraction, element-wise multiplication, and division of two matrices have to feature the exact same dimensions, otherwise you're going to get an error. Taking the transpose of a matrix. So as defined in the previous videos, the transpose is where we take the rows of a matrix and the columns of a matrix and switch them around. So our rows become columns and our columns become rows. So when I take the transpose of matrix C, and the way that you can specify that is by using the T function, so just T in parentheses, and I want to input my matrix C. Let's go back to what matrix C was. And this is what it looks like. Matrix C is a 20 by 5 matrix with 20 rows and 5 columns. So by taking the transpose of matrix C, I now have 5 rows, 20 columns. Rows become columns, columns become rows. And here's what it looks like. So we changed matrix C from being a long matrix, right, an extremely vertical matrix of 20 rows. We converted it to being a very wide matrix, or a horizontal matrix, where it has only 5 rows and now 20 columns. Taking the inverse of a matrix is kind of a complicated process. I'm not going to work out the details by hand, but this is essentially the best that we can do when it comes to dividing matrices against one another. But it involves the determinant of a matrix, so if you remember from linear algebra, and it's perfectly fine if you don't, the determinant is simply a scaling value. It shows how much a matrix is transformed from its base or unit matrix. So the determinant has to be non-zero. And in order for a matrix to have a determinant, it has to be linearly independent. It has to be square. So a square matrix is where we have 10 rows, 10 columns, 5 rows, 5 columns, symmetric number, equivalent number of rows, and equivalent number of columns. A matrix is of full rank, and what do I mean by full rank? It means that all of its rows, all of its columns are linearly independent of one another. So only under these conditions can we take the inverse of a matrix. If these conditions do not exist, we cannot take the inverse. So let's try to take the inverse of A. And we take the inverse by specifying the solve function. Seems like it worked, and it did. So A was a square matrix. Since we generated random samples, random data observations from a uniform distribution, they were independent of one another, so there is no trouble with dependencies. So we satisfied all the assumptions necessary for taking the inverse of a matrix, and we were able to do it. And the typical way we write or abbreviate the inverse of a matrix is A, and then with the superscript -1. That's how we indicate the inverse of a matrix. Now let's determine the rank of a matrix. And the rank, again, if you look back up here, it describes the number of linearly independent rows and columns. So if we have a matrix of full rank, it means that this number that we get, and this is again with respect to matrix A, it has 10. How many columns does A have? Oh, it has 10 columns. How many rows does A have? It has 10 rows. We have a 10 by 10 matrix with a rank of 10. This indicates that matrix A has full rank. full rank. Thus it has independent rows and independent columns. So it satisfied the linear independence, it is square, it has a non-zero determinant, and it's a full rank. That's how we were able to take the inverse of a matrix. So the rank simply describes how many linearly independent columns and rows you have in a matrix. And if you have full rank, that means you have a linearly independent matrix. Similarly, the determinant of a matrix is a concept related to inverse linear independencies, but the determinant is a scaling value. So you have to have a square matrix, you have to have a linearly independent matrix, and all the determinant shows is it's like a stretching factor. It's a scalar, it's one number, and it shows how much a matrix has stretched from its base matrix. So if we take the determinant of A, we have 2.630847 all the way for a very long decimal number. The determinant of B, again, is a single scalar value, so the determinant is a scalar value. Once you get into higher order matrices, determinant becomes very difficult to calculate, so this is a great way of doing it. Does the determinant exist for C? Now remember that C is a 20 by 5 matrix, so it has 20 rows, 5 columns. Obviously we're going to have linearly dependent rows and columns, and it is not a square matrix. So we're going to have an error, and this is how it tells you we have an error in calculating the determinant. X must be a square matrix. Now when it refers to X, it's just referring to our matrix C. Now let's perform the eigendecomposition of a matrix. And an eigendecomposition is a way to decompose a square matrix. So all an eigendecomposition does is it's an effective method for viewing a matrix transformation as a series of eigenvalues and eigenvectors. An eigenvalue showing how much its corresponding vector, also called an eigenvector, stretches in response to that transformation. Again, another complex process, but R does it relatively efficiently. So let's take the eigendecomposition of A, and we see our eigenvalues all right here. And actually in A we have real and imaginary eigenvalues, so that's an interesting situation. Now let's construct a matrix storing these eigenvalues along its main diagonal. So we construct a diagonal matrix, and we use that by using the diagonal function, and we're going to round these eigenvalues, which we can see here as containing real and imaginary values, to 2 decimal places. And in doing that, running it, and viewing it, here we have our eigenvalues rounded to 2 decimal places lying along the main diagonal of this matrix. And this was done using the diag function in R. So let's construct a matrix of unit eigenvectors. The way we do that is we take our eigenvectors, which we stored in the operation eigen-A, and we call it by using the $ vectors. And we store these in eigenvecmat, again just an arbitrarily named matrix, and when we view that, here we have our eigenvectors associated with the decomposition. So these are in their unit form, so these are standardized eigenvectors. And if we wanted to stretch these vectors or see how much these eigenvector components stretch, we will multiply them by the square root of the eigenvalue. But that is a matrix of unit or standardized eigenvectors. Let's try taking the eigendecomposition of C. Will it work? No, it won't, because an eigendecomposition can only be performed on a square matrix. Singular value decomposition, or taking the SVD of a matrix, is a more general approach to eigendecomposition, in that a matrix doesn't have to be square, it can be rectangular, and you can still perform the singular value decomposition or factorization of a matrix. So let's take the singular value decomposition of matrix A. We use that by calling the SVD function, We're going to store it in SVDA, which is a list of 3 distinct objects. Those 3 distinct objects form a list of a vector of scalars and 2 matrices called U and V. This is part of the singular value decomposition. I don't want to get into that now because it's extremely complex, but if you ever need to take the singular value decomposition of a matrix, this is how you can do it. Now let's try it for a non-square matrix or a rectangular matrix, matrix C. We'll store that in C. In our output we have no errors. And when I take a look, here we have a 20 by 5 matrix, a 5 by 5 matrix, and a vector of singular values that has a length of 5 with 5 singular values forming it. So SVD is just a general extension of eigendecomposition beyond a square matrix. So we did quite a lot in this video. Feel free to pause, go back, brush up on any topics you may be unsure of, maybe review some linear algebra concepts, but in the next section we'll be taking a look at using the apply function to deal with the sum of squared deviations away from a certain variable. And that's a statistical concept that comes up a lot in regression, especially linear regression. So it's a handy concept to have, and it's going to be using the apply function. But until then, see you soon. I'm Ryan Lafler, and this was for the book Climate Mathematics, Theory and Application, corresponding to Chapter 2. Thank you.